Hello, welcome to Mr. CFD. This video presents an analysis and discussion of the results of this numerical validation product based on the paper laminar flow and heat transfer in U-bands. First of all, let's discuss the velocity distribution. Velocity contour shows a clear variation in fluid speed throughout the U-band. The fluid velocity is highest at the center of the pipe and decreases towards the walls due to the no-slip condition. In the bend region, there is a noticeable increase in velocity on the outer radius of the curve, while the inner radius experiences lower velocities. This is due to the centrifugal force acting on the fluid as it navigates the bend, pushing it towards the outer wall. Now we want to see how temperature is distributed in the domain. Temperature contour reveals a gradual increase in fluid temperature as it flows through the pipe. This is consistent with the constant heat flux boundary condition applied to the pipe wall. The temperature is lower at the inlet and increases towards the outlet. Interestingly, there is a slight temperature variation across the pipe cross-section, particularly in the bend region, indicating the influence of secondary flows on heat transfer. This is consistent with the base paper's discussion on the disruption of thermal boundary layers in curved sections. Let's take a look at pressure distribution. The pressure contour shows a gradual decrease in pressure from the inlet to the outlet, which is expected due to frictional losses. There is a notable pressure increase on the outer radius of the bend and a decrease on the inner radius. This pressure gradient across the bend is responsible for generating secondary flows, which enhance mixing and heat transfer. The close match between this product results and the reference work, particularly in the dimensionless pressure graph, validates the accuracy of the simulation methodology. The graph comparing the present work with the reference work shows excellent agreement. Both curves follow the same trend, with a gradual increase in dimensionless temperature as the dimensionless length increases. There is a sharp change in the curve around S star for dimensionless length of 0.5, which likely corresponds to the bend region, matching the observations in the base paper about the impact of curvature on temperature distribution. Overall, the simulation captures the complex fluid dynamics and heat transfer phenomena in U-bend pipe. The results demonstrate the formation of secondary flows in the bend region, evidenced by the velocity and pressure distributions. Enhanced heat transfer in the bend due to increased mixing and turbulence. The impact of centrifugal forces on the flow pattern and temperature distribution. And finally, the accuracy of the simulation as validated by the close agreement with the reference work. These findings are crucial for optimizing heat exchanger designs, particularly those involving bent pipes or complex geometries. The study highlights the importance of considering local flow characteristics when predicting heat transfer performance in such systems. Hope this video is helpful for you. To benefit from Mr. CFD services including simulation, consultation, and training, visit our website www.mrcfd.com or contact us via info@mrcfd.com.